In this segment, we're going to construct the graphs of inequalities involving two variables. Now, in a previous chapter, when we examined inequalities involving one variable, we could illustrate the situation or construct graphs like that on a number line. But here, our graphs are going to be on a coordinate plane because they involve two variables. And the solution set, the picture of all the solutions to these inequalities in two variables will turn out to be a region of our coordinate plane. We begin the process like this. Suppose we want to construct the graph of this inequality. Now the graph, you know, is a picture of the entire solution set for this inequality, and solutions are values of x and y that will cause the statement to be true. So that fundamentally is what we're after here. We begin by writing the related equation. An equation related to this is simply take the inequality and write the equation. That is, write minus x plus 2y is equal to 4. Now the graph of this equation is a line, and it turns out that that line is the border of the solution region for the inequality. All right, to construct the graph, we've solved for y. So we would have, let's see, 2y is equal to x plus 4. Dividing through by 2, I would find y equals, now I'm dividing here by 2, and x over 2 is the same as 1/2 x. And I want to write it like this so that I can see the distinct slope of the line that I'm dealing with, because I'm going to use the slope-intercept form. When I divide here by 2, I get 2. All right, let's see, slope-intercept form. I have a y-intercept at 2 and a slope of 1/2, so I can go over and construct the graph rather quickly. I have, let's see, intercept of 2. Slope of 1/2 means a rise of 1 and a run of 2. Rise 1, run 2, up 1 over 2. And in the other direction, I can generate points in a similar way. Down 1 over 2, down 1 over 2, and so on. Okay, and the graph then looks like this. Now, as I say, this is the border of the solution region. Now, it turns out that we identify which region is the solution region by taking a test point. And a rather easy test point is the origin of the coordinate plane, simply because when x is 0 and y is 0, they're easy to plug into the original inequality. And that's what we're going to do. So we take the origin, the coordinates of the origin, 0, 0, and we plug into the original inequality. And let's see, if x is 0 and y is 0, we get 0, 0. Is 0 greater than or equal to 4? Is 0 greater than or equal to 4? No, 0 is less than 4. So this point is not part of the solution region, and therefore no point over here is a part of the solution region, and the solution region then lies on the other side of the line. So the solution region then is up here. And then I would shade to illustrate that this is the solution region. And it's a solution region because for every point in this region, we could take the coordinates of any point and put it back into the original inequality, and it would make that inequality true. Now, the line itself, let's talk about the border itself. The border line itself is part of the solution region because the original inequality says greater than or equal to. Now, the equal to part we graphed as the border line, you see. And so this, we know that the line is the solution to the equation. The equation is part of this non-strict inequality. So the border line is part of the solution region. Now, if the border line was not part of the solution region, we would make it a dotted line. Consider this inequality. We have y is less than negative x squared plus 3. We can almost imagine the graph of this using our ideas for transformations, but let's be very careful with it and construct a table of values. I'll write the related equation, just replace the inequality symbol with an equal sign, and now I want to construct the graph of this. And this curve will be the border of a solution region, non-solution regions, you see. All right, so then I'll make a table of values. I'll let x take on values 0, plus or minus 1, plus or minus 2, plus or minus 3. And these are the y values that come out of that. All right, let's plot the points. So let's see, we have 0 goes to 1, 2, 3. Plus or minus 1 goes to 2. Plus or minus 2 goes to negative 1. Plus or minus 3 goes to negative 6. And now I'll construct the graph. When I construct the graph, though, I'm going to make that graph dotted because we have a strict inequality. And so that the line, the parabolic curve itself, is not a part of the solution region. Now notice that y is strictly less than this expression. And so that strict inequality tells us that we have a dotted border and not a solid border. Well, once again, we can use the origin as a test point for that inequality. Let's see, the coordinates would be 0, 0. If I put 0, 0 in place of x and y, I would have 0 is less than 3. That's true. So this then is the solution region for this inequality. Now I can shade here if I'd like. Let's see, I'll shade in this region. What if we consider the notion of using the two inequalities at the same time? What if we want solutions to a system of inequalities? Now, the system would be, let's see, it would be this inequality that we started with over here, and also the one that we graphed from over there. The other inequality would be y is less than negative x squared plus 3. Consider this system of inequalities. What is the region? What are the solutions to this system of inequalities? And it would be a region in the coordinate plane. And it just turns out to be the region where it's kind of like the truth region for this, so the shaded region associated with this inequality and the shaded region associated with this one. And where do they overlap? Well, remember the solution region for the line was above the line. The solution region for the parabolic curve was below the parabolic curve. So the region right in here then would be a solution region for the system of inequalities. Now, notice that we have a dotted, I don't know if you can see this or not, but the top of this solution region is dotted, but yet the bottom of it is solid. Interesting kind of configuration here. By the way, sometimes to find the side of the figure that is going to be the solution region, you can reason like this. Come back over here and look at this inequality. We have y is less than this expression. Okay, this means vertical distances. Y stands for or implies vertical distances. So what vertical distances are less than this rascal? Now this is the parabolic curve, you see. So we want vertical distances below the parabolic curve. That's one way to interpret that situation. Doesn't always, it's not real convenient to use it in all cases, but we could have used it in both of these here when we had solved for y, remember. Okay. In this next system of inequalities, we might notice first that we have non-strict inequalities in both cases. So that means that the graphs are going to be solid. And those borders, those solid borders, are going to be part of the solution regions associated with the two inequalities. Okay, we write the related equation for each of these and construct the graphs. As soon as we write the related equation for the first one, we recognize this as the equation associated with a circle. The circle has its center at the origin and its radius is 5. I have constructed the graph of that circle. Now we might consider the solution region here. Notice the circle subdivides the coordinate plane into two regions, one region inside the circle and the other region outside the circle. So which is the solution region? Well, a nice test point once again is the origin. The coordinates are 0, 0. We pop those values in place of x and y here. We have 0 is less than or equal to 25. That's true, so the origin is part of the solution region, and therefore all of the points inside the circle are part of the solution region. For the other figure, well, let's see, we have 4x minus 3y equals 0 as the related equation. Now we'd like to solve this. One way to do it is to put it into the slope-intercept form. I'll divide through by negative 3. When I divide here by negative 3, I have simply y. When I divide on the right by negative 3, I have this. Now I'd probably think about it as 4/3 x. You see the distinct coefficient telling me about the slope. Now in slope-intercept form, the y-intercept is 0. There's no constant over here, so we think of it as simply plus 0. So if the y-intercept is 0, then that's the origin. and the slope is 4/3. Well, so from the origin, we're going to go up 4 and over 3. All right, let's do that. So here's the y-intercept, and from this point, rise 1, 2, 3, 4, over 1, 2, 3. And we can do the same thing again, up 4 over 3. But let's go in the other direction. Down 4 over 3. And now the graph. And once again, that graph is solid because we have non-strict inequalities. Okay, so there's the graph. Now, which side of the line are we talking about? Uh-oh, we can't use the origin as a test point because the graph goes through the origin. So we need a point on either side. Well, let's see. How about the point 1 and then up 1, 2, 3? The point 1, 3. All right. Do the coordinates of this point make that inequality true or false? So let's go over and see. All right, so we're up here. If x is 1, this becomes 4. If y is 3, this becomes minus 9. So let's see. 4 minus 9, that's negative. A negative value less than or equal to 0? Yes, that's true. So this point is in the solution region bordered by this line. So the points on this side of the line solve the inequality associated with this border. And let's see, for the whole system then, we want to be inside the circle, but on that side of the line, oh, we shade then in this region. Consider this system. We have x is greater than 2, and we have this other inequality which looks a little funny maybe. Well, let's see, for the x is greater than 2, the related equation is x equals 2. Now we recognize this as having a graph which is a vertical line. So we're going to make a vertical line at x equals 2. Okay, fine. Now is that vertical line going to be dotted or solid? Well, I see a strict inequality here, so we're going to make a dotted line. All right, so let's go over here and do that. So we have a dotted line. This is the line x equals 2. All right, and it's dotted because it's a strict inequality. Now we're thinking about test points here. We can use the origin as a test point. The coordinates are 0, 0. Back over here, if x is 0, now there's no y to plug in, but that doesn't make any difference. If x is replaced with 0, we have 0 is greater than 2. That's not true. So the solution region then does not contain the origin. The solution region is on the other side. So the solution region is over here. All right, consider the other inequality. We have this. Now, the related equation, there are all kinds of ways of dealing with this, but I think the simplest thing to do is just to make a table of values. Now, before we even make the table of values, we could solve for y. But I think we can see through this rather easily without even doing that. If x is replaced with 0, we have, let's see, minus 0 plus 4. So y squared equals 4. Now by the square root property, you know, if y squared is 4, then y is plus or minus the square root of 4. So y then is plus or minus 2. All right, what if x is 4? Now I'm trying to choose my points wisely here so that this will kind of come out evenly and I won't get irrational values. But if x is replaced with 4, I have minus 4 plus 4, that's 0. So if y squared is 0, then y needs to be 0. What about 3? Well, let's see. If x is 3, I have minus 3 plus 4, that's 1. If y squared is 1, then y is plus or minus the square root of 1, or y is plus or minus 1. Let's plot these points and see if it's enough to tell us about the nature of the graph. We have, let's see, 0 goes to plus or minus 2. 0 goes to plus and minus 2. Now, we probably know from experience that this is going to be a parabolic curve that opens left or right. And we're going to discover how it opens here right quick. If x is 4, y is 0. If x is 4, 0. So we're going this way. All right, then if x is 3, y is plus or minus 1. So it looks like this. Now let me think about, as I draw this, I want to think a little bit about whether it's dotted or solid. I'll look up here and see, oh, okay, this is less than or equal to. So that means then that we have a solid border. And the graph looks about like that. Okay. Now, which side? We know that for the line now, the solution region is to the right. But what about for the parabolic curve? Now, let's consider the two cases here. We're thinking about a region that is within the parabola here, or if the solution region is outside. Now, if the solution region were outside and we're solving the system of inequalities, we would want the points outside of the parabola, sort of, and to the right of this line. So it would be, solution region would be here, kind of go around this little end of our parabolic curve. Now, on the other hand, if the solution region is inside, we would want the inside of the parabola and to the right of our dotted line, and that would just be this little region. Let's see which one it is. Now, for the parabolic curve, we can use the origin as a test point. So replacing x and y with zeros here, we would get 0 is less than or equal to 4. That's true, so the origin is part of the solution region. The solution region is in here. And for the system, we want, let's see, the overlap of this solution region with that solution region, and so the region of solution for the system is right in here. Here's a system involving 3 inequalities. A couple of the inequalities look to be relatively simple. The idea here is exactly as it has been in the past. That is, for each of the inequalities, we're going to write a related equation. We're going to identify a solution region accordingly, and we're looking for the overlap of the 3 solution regions as the solution for the entire system. The equation related to the first inequality is x plus y equals 5. Solving for y, I get y is negative x plus 5. And using the slope-intercept idea, I have an intercept at 5 and a slope of negative 1. So an intercept at 1, 2, 3, 4, 5, a slope of negative 1 means, well, I can look at it in one of 2 ways. I can either look at it as 1 over negative 1 for rise over run purposes, or I can look at it as negative 1 over 1. You see, so if I use this idea of 1, negative 1, 1, negative 1, 1, negative 1, and so on. I run down this way, and then the other one will give me points on the other side, negative 1, 1, negative 1, 1, and so on. Okay, now I'm kind of thinking about, is this line going to be dotted or solid? I look back over here, non-strict inequality, solid line. The line is, that border line is part of the solution region associated with this inequality. That's the idea. All right, now which side do I want to shade? I think I'm going to go ahead and do the shading here because I have a lot of things to keep up with. I have 3 different regions that are going to overlap here. All right, think about the origin as a test point. If x and y are replaced with 0, we have 0 is less than or equal to 5. And that's certainly true. So the origin is part of the solution region, so we're going to shade on this side of the line. Let me try to show that lightly like this. All right, now for the other 2. The related equation here is x is equal to 2. And we know that's a vertical line going through x equals 2. Okay, now which side are we going to shade? And let me go ahead and draw the line. All right, x equals 2 right here. It's a solid line because we have a non-strict inequality. Now, to determine solution region, we can really do it intuitively. We don't need a test point here so much because x is a horizontal distance. So we're graphing here horizontal distances which are greater than or equal to 2. So we're going to be shading on the right side of that line. So we shade over here. So this is the idea. Now for the other one, we have y is greater than or equal to 0. The related equation, y equals 0. We know that to be the x-axis. So the x-axis. Now, on which side do we shade? Well, let's see. Vertical distances greater than or equal to 0, that's above the x-axis. So we're thinking about above the x-axis, to the right of this line, and below this other line. So the solution region to the system of inequalities is the region inside this triangle. Now, it turns out that the graphing calculator can help us to illustrate the solution region. It doesn't actually solve the system for us, but it can shade this solution region for us. Let's have a look. I want to show you 2 techniques for seeing that shaded region that we were just looking at. Remember, one inequality was y is less than or equal to negative x plus 5. So I've entered y equals negative x plus 5, and here is its graph on particular window settings. And now what we'd like to see, though, is a shaded region. It turns out that this graphing calculator, the TI-83, is capable of shading below a graph or above a graph. And here I'm pressing enter with the icon over here on the left side. And as I press enter, different options are becoming available. This option is one which shades above the graph, and this is an option that shades below the graph. And here's what the graph looks like with the shading below. Now, we are not achieving the shaded region. This is not the entire shaded region that we were looking for, but by using this kind of technique, we can continue by entering y equals 0 as another equation, and let's shade above this because we wanted the inequality y is greater than or equal to 0. So I'll go over to the left, and I will elect or select the item that is shading above, and now here's the graph with that one on board. So we're shading everything above the x-axis and everything below that diagonal line. Now there's just one other element involved in the situation, and that is that we want the region which is greater than, where x is greater than or equal to 2. Now we can't actually achieve that here very easily. However, we can draw a vertical line, and we can do that by pressing second quit. And I'm going to enter the draw menu by pressing second and then draw. It's the second function on the program key. Now I'd like to draw a vertical line. That's item number 4. And I want a vertical line at x equals 2. And now I'll press enter. Now notice here is the vertical line x equals 2. So we know from our experience that we want x is greater than 2, so we want to be to the right of that line, and we want the overlapped section, the shaded region, for the other two. So we're talking about this region. Now there's another technique that we can utilize here, and it is this. Let me take off these two functions. I'm going to just clear these off, and I'm going to make a creative window setting here. I know that I'd like for x to be greater than 2. So I'll set the x minimum at 2. And now I know I want y to be greater than or equal to 0, so I'll set the y minimum at 0. And now I'll press second quit and go to the main menu, and I'll clear out the vertical line of 2, and I would like to enter another draw menu known as shade. So I'll press second draw, and I want the shade item, so I'll press number 7 at the bottom of your screen. Now, the protocol for shading is this, that you're supposed to enter the bottom of the shaded region as a first item, and then the top of the shaded region as a second item. So I'm going to enter 0 for the bottom. Now this is like entering y equals 0, you see, for the bottom of the shaded region. And now a comma belongs in between. And then we want the top of the shaded region, and that top is defined by the line negative x plus 5. So negative x plus 5 is the top. I'll close the parenthesis and press enter. Don't press graph, press enter. And now, you see, the window settings have allowed us to achieve a situation where this is the x minimum at 2, you see, so, and this is the y minimum at 0. And so we have exactly the shaded region that we were looking for on our coordinate plane earlier. Now, what's tough about this is that we can't see exactly where we are in the coordinate plane. We are only seeing a particular shaded region. But nonetheless, that shaded region can be seen in a couple of ways.